not done a binarization of that, straight away you cannot apply any kind of machine learning algos. The pipeline will break, the programming will break. So in those instances, we have to convert and basically do a transformation, convert it to a binary variable, then change the data type to integer, then the algorithm will work on top of it. Okay, so yeah, so let's look at this. What we're trying to do, load transformations. Okay, so this data set also something we have to load. Births, train, CSV, GJ. Okay, let's see if we have this data table here. File store, tables. This data we have. Births underscore train underscore CSV, DC6BEZ something something. Okay, that is one. Then this is a transformed one. So two different data sets we have here. Do we have the raw data also somewhere? Let's see. No. That's fine. So we can use this one. Let's check this one. Okay, this is fine. This is the output from the previous module. Okay. So this part I will take it to the top and move up. Okay. First we'll import the data. Schema is not defined. This is important now. You are importing a CSV file, which is in the form of a compressed zip file, and we want to read that. So one way is that first to define the schema somewhere or infer schema equal to true. Two ways we can do, right? So here we can simply remove it so that it becomes infer schema equal to true. Okay. Path must be absolute. So there is a difference in the path. Okay. Go to file store. This one. This is API format. Select a path to copy. There is no difference. Copy. This is fine. DBFS file store tables. This does not exist. Path does not exist. Okay, why this is so? Just a moment. Just let me check this. This should be working. Where this file path is not working. Okay. I'll just remove the DBFS from this. This works. Next, just add birds dot head 3 records. Okay. Or we can do show which is in tabular format, or we can do take. Okay. So now we can say infant alive at report no, birth year 2015, birth month 2, birthplace 1, etc. So this is one record. Okay. Let's look at one only. Here, automatically this is one record. and we are trying to read this data without a schema. Okay, so then we can define the schema. Currently, we don't know what data type it is. Now, simply you can just do print schema string, almost all are string now. Almost, yeah. So all the variables are in string format. Okay. So we need to define all of them are string. So we need to change certain data types over here. As an example, birth year it is string, but it should be ideally a number. So it should be integer. That is why we have to first import the data types. So PySpark SQL types as type, and then you define. So this column should be string, this column should be integer, this should be integer, like this. We just create a mapping for each of the columns, what data type it is, right? So we just do type dot string types, type dot integer type, etc. We just define it. Then you can just use struct type, struct field, and just write a list comprehension method to run it. Now this thing we need to apply on this particular import statement here. So what we are going to do now is that add and just make schema equal to schema. Now then we can check once more. Print schema and just check the data type. So birth year now integer, birth month is also now integer. It is fine. Good to go. Now recode the dictionary. So YNU, Y equal to 1, N equal to 0, U equal to 0. So YNU means Y is yes, N is no, U is unknown. So unknown and no both are coded as 0. Y yes should be coded as 1. So any kind of a binary outcome is there in this particular data set, we have to change it. So that's why this recoding is required. Now we run this. Then we'll go to the selection of features. There are certain features which need either, so question as an example here, infant alive at a report, either 1 or 0. It cannot be unknown. If it is unknown, it should be 0. We don't know, right? So we'll drop all the features that relate to the infant, and how all those features that is related to the infant, it may have 3 outcomes. So we need to code it as 0 and 1. So here selected features, the way selection, and create another data frame. It's called births underscore trimmed data frame. Then what we're trying to do next is recode. So recode the dictionary, and that is one. Then correct the, for example here, correct the data types, right? So when function column feet not equal to 99, function column feet. So there is a feet column somewhere in this data frame. This is fine. Where is feet? Somewhere it is there. This is recoded in GST PST. Find which column it is referring to currently. Column and key, recode the dictionary, which is fine. This one is a function call. Okay. So basically anything when the function is not equal to 99. So 99 is a dummy coding. If it is not equal to 99, then it is 1, otherwise it is 0. Okay. Then you are creating a function UDF. Now this is important. The user defined function, the role of user defined function is that you can apply this function straight away on the data frame itself. So instead of a repetitive application of a function, you can create a standard UDF, which is known as Spark UDF. So this Spark UDF user defined function you can apply. So function.udf, recode is a function and type should be integer. You run this, then you do a trimmed here, correct. Okay, this column it is being applied with column CIG before and CIG before, so correct CIG. So there are some inconsistencies in this CIG column. Okay, that's what we're trying to correct it or recode it. So correct CIG, and we are just doing at one go. We are doing now. This is one of the way. You remember in the previous session, I told you that if I have to create multiple columns and append it to the data frame, I probably have to write it multiple times. So I'll say this underscore df5 and with column this, then you store it as another data frame. Then again take that as a reference, then create another data frame. So by the time you create 4 columns, you will be end up getting 5 different data frames in your console. So in order to avoid that process, you can do or you can use multiple with column statements here. So you can create multiple, like here in this case, 4 columns at one go and append it to one data frame itself. Okay. Now this one we can run it.
No, but what are we doing in this function? I didn't get this.
This one, what we are doing?
Yeah.
Okay. Now CIG before, CIG1, TRI, etc. So this is some dummy coded columns. Okay. I think I have to create a new line here. First, let's look at the data. It is births. This is one record. 0. Where it is? Sorry. This is one record. This is the column name. This is the value. Infant alive at report? No. Birth year 2015. So key and value. Keys are basically column headers. Values are corresponding to this particular row number, this whatever is being picked up as first row. Okay. Birthplace 1, mother age is 29, mother race is coded as 3, education is coded as 9, father combined is father education 9, so something like this. So these are all the values associated with the infant's data, right? Now in this case, some of the columns may have values like yes, no, and unknown. 3 possibilities are there. So most of the places you can see no. No. But there are certain places where it could be present as U. U means unknown, right? So we have to convert the string values that is present in the data to a numeric format. Now this part, the recode dictionary part, basically will take care of, or it will be applied across different columns wherever there is a combination of Y and U, yes, no, unknown, then it should be coded to 1 and 0. Okay, this part is clear. The next part is basically, if you look at those 3 columns, so there is some dummy coded things. Those 3 columns you can see CIG before 99. What is 99? CIG 1 try 99. This is 99. This is 99. So 99 and 999. Here you can see mother pre-weight 999. Not possible. Absolutely, somebody's weight would be 999. That is not possible. Which means when data is not available, they have done a coding of 999. And mother weight gain 99. This is also, if data is not available, this is a standard practice in data analytics industry, which is like a very old practice. If data is not available, then you make it 99 or triple nine or some dummy coded thing that you have to do, which could possibly impact our analysis. Now, if you see here, the same column here, it is integer, right? So integer 99 or triple nine do not have any relevancy here because it's not possible and it's a dummy coded thing. So we have to replace it or recode it. To do that replacement, what we are trying to do here is we are trying to apply when function column feet. So feet means the list of columns that we have been selecting over here. So if it is not equal to 99, apply the function call, which means keep the data as it is. Otherwise, make it 0, which means wherever it is 99, make the data as 0. Okay. And this thing need to be applied only on those 4 columns. CIG before, and then here you can just do, you are modifying it. Birth transformed is the new RDD or new Spark data frame on which you are creating multiple new columns. These columns are existing in your old data frame, which is births underscore trimmed. Okay. So births and births underscore trimmed will have all those columns ready. Now, when you do a transformed form of this particular data, this with column syntax can be used and this column could be used, and then you can say correct underscore CIG function that you are, this correct underscore CIG function you are applying on this particular column, and you want to store it as a new column which can be called as CIG underscore before in this birth underscore transformed data set. Is this clear?
Right. So it will be the same column only when the values are not equals to 99, then the value will be restored, or else it will be 0, right? But I mean, we'll have only one column called a CIG before CIG1, right?
Correct.
Right. Okay.
Okay. Next is, this is
But triple nine we are not handling.
triple nine. Yes, we have not handled so far. That also requires similar kind of function. That is also another kind of redundancy which we have to remove. Okay. Now, this is again a function call using enumerate function. Now we are trimming the data set again. So what we are trying to do, column name and a data type for columns in the birth trimmed schema. That's your columns function. Then you create yes, no, unknown columns. Then apply this, right? So which function you are going to apply? You are going to apply this recode function. The recode function is nothing but the recode dictionary that we have coded over here by a new key. Okay. So applying that, we have to modify the data. Then next we can print and see the results. Select this particular column, admission column, apply this function rec underscore integer on this column, then use the function new key and create a new column known as recode take 5. This is the old, this column is old column, this column is the new column. When it is yes, it is 1. When it is no, it is 0. When it is unknown, it is also 0. So basically it transforms all the yes, no, unknown columns, right, using a standard transformation so that all yes, no, unknown columns would be in the form of 1 and 0. Right, clear? Okay.
Okay, but question over here, Pradeepta. I mean, All these things we are doing it manually, like the recoding and all. So like in machine learning, normal Python coding, we have the coding transformation functions. So those kind of functions are not available, right? Is it?
That will not work here. It
Okay,
has to
because
be PySpark function.
yeah, I mean, any like typical those kind of function where we one hot encode all the columns.
Mhm. No,
Oh,
those functions will not work in distributed computing.
okay.
And because here, and this code is little older, that's why this way we are doing a recoding, right? But today we can use map function. Map and reduce function can be used to do a mapping from 1 to yes to 1, no to 0, unknown to 0. Those kind of functions we can do. So we can play with the existing PySpark functions. Multiple ways are there, like that is map function is one, flat map is one, then reshape is one, replace is one, and then of course this is also another one.
Okay.
Okay. Similarly, we can add these columns to births underscore transformed. Now this is how it looks. All yes no type columns will look like this. Zeros and ones binary form, which is easy. Then we can apply descriptive statistics. So these are some of the numeric columns that has been picked up. Births underscore transformed is the dataset on which we are going to run this. Select all the numeric columns which is provided in this list and read it as RDD. And on top of this RDD, do a mapping. So mapping of a row E for E in the row, which means each row you take at one time and do select the numeric columns and append and run this transformation. Then what you do, this numeric identity that you are creating over here, you want to get the column statistics. So st PySpark mlib statistics as st and st.statistics column statistics of all the numerical RDDs. You can store it as mlib statistics. Then what you can do for column m and v in zip file, which has three things: numeric column, arithmetic mean, and variance. So mean, variance, and numeric columns, all three need to be picked up. Column name, m, mean, and square root of v, which is variance. All three things need to be printed. So this is mother age years, 28.30 is arithmetic mean. Standard deviation is or variance is 6.08. Like this for all numeric columns, you can see two values. So basically we are computing the mean and variance of all the numeric columns in this data frame. Clear? Any questions? Okay. Then what happens to the categorical columns? Numerical columns, we get the mean and variance. For categorical columns, we need to get some statistics, descriptive statistics as well. So first we'll do a selection of a categorical columns automatically. So basically, whichever is not numeric, that is becoming your categorical column. So E for E in transformed data, birth transformed data frame, dot columns, pick up the columns. If E not in numeric column. So there is a numeric underscore calls list. Anything that is not there in this list is becoming your categorical. So select the data frame, do a selection of all the categorical columns, convert it to RDD, apply the map function over there, and you extract the E for E in this particular row. So each row would be picked up. Now that becomes your categorical RDD. Then what you do, you apply the enumerate function over here for I column in enumerate categorical columns. Add aggregation statistics, which is categorical RDD, group by the row and map the row and length of row. Then print the column name COL, that's the basically column name, sorted aggregate dot collect and key equal to lambda, reverse equal to true, which means in descending order. Okay. Similarly, we can do correlations as well. Correlations is basically taking two combinations of columns, numeric columns, and printing a matrix. Here, CIG before 2, CIG first trial, 83% correlation. CIG before 2, CIG 2 trial, 72%. That is so on and so forth till all the columns are exhausted. Now that becomes your correlations matrix. Now we can drop most highly correlated features. That's manual process. You have to figure out what is the definition of highly correlated. If it is more than 85% or 80% and we call it a highly correlation, you can drop it based on your use cases. Okay, any questions so far?
So have we selected these features?
How we have selected these features?
I mean, based on that correlation, right?
Yes.
So here cutoff is 85.
80%. Anything greater than 80%. Now these are all 60. This is 89. This is 89, 87, 87, 83, 83. So 1, 2, 3, 4, 5, 6. Okay. Next is about once we get the categorical columns and numeric columns processed, then aggregation RDD, which means for categorical in categorical columns, do a group by at column level. Create a pivot view of it and do a count based on all those columns selected on the pivot itself. Then you define a function aggregation on the RDD. So aggregate.rdd map function, flat map, and do a collect. Right? What we're trying to do here is we are trying to perform a statistical test over here. Now the statistical test is nothing but it is on a cross tabulation view of the data. Aggregate collect 0, and that is basically your aggregated matrix. Then you apply chi-square test. Chi-square test is going to be applicable on categorical data. Chi-square test of independence. From this, you are extracting the p-value. Okay. Similar, the next step is about creating the final data set. Okay. Is it clear till now? If you have any questions, I'll explain it.
Pivot.
Sorry.
Pivot.
It's clear, right? Okay. Next one is label point. This concept is very important. Please pay attention to this when we are doing a regression. Okay, so I'll go to Excel once again. Just give me 5 minutes, please. Hello everyone. Sorry guys, and there was something I had to attend. Okay, now what I was discussing before, uh, level point. What is level point? So typically in machine learning, what we do, we have a target and we have input features, right? This is also known as input features. I hope it is visible, right? Target can be regression, it can be classification. For a regression, it would be continuous variable. For a classification, it would be binary or multi-class classification, right? So target can be 1 or 0, 1, 0, 0, 1, 1, 0, 0, 0. It can be anything like this. Okay. Feature input is basically nothing but it's going to be, suppose first is age, gender, income. Let's take 3 features. Okay. So in Spark, what happens? All the features would be combined together as one column. Your target will be one column. All features would be comma separated, but this would be one column. This is how the API would need the data to be arranged, right? In normal pandas data frame, when you are training machine learning models, you can have 3 features here: age, income, gender, etc. You can have 3 features. However, in this Spark APIs, you need to provide this as one feature. So to do this, there is a specific syntax which is called level point. Okay, how the level point works is basically it combines the information together. This does 1 comma square bracket 12 0 120 square bracket ends. This is how the data would go to the algo. This is called a level point. Is it clear?
Yeah.
Yeah, this is what we are trying to do over here. So from PySpark mlib feature, get the feature transformation ft, get the regression module as a reg, do a hashing feature transformation. Hashing feature transformation is binary transformation of all the columns. Now you are going to apply birth transformed is the data frame, get it as RDD, do a map here. Now mapping could be hashing transform row 1 to array format if column equal to birthplace, else row I. For I and column in enumerate all the features to keep. Then again apply map function using lambda function row E if type E is equal to integer, else E for E in the row. Same thing here, map row item for sublist in row for item in the sublist. So then again map function lambda level point. So finally we are doing row 0 vectors dense. Now another concept is dense vector, sparse vector. Dense vector is basically what is sparsity? Sparsity means if you have a matrix of 10 cross 10, only 2 elements are there, rest all elements are 0. Now that is almost like you can say 98% sparse, right? If you have a 10 cross 10 matrix, which means 100 cells are there, right? Now out of 100 cells, only 2 cells are having values greater than 0. Rest all are 0, which means the entire matrix is called a sparse matrix. In those scenarios, right, sparse matrix, the algo will fail. So you have to convert the array to a dense matrix. Now you have to tell the algo, regression algo, that this is a dense matrix, then only the algo will work. Okay, that is what we are doing. First to vectorize, linear vectorization. You do a vectorize, then create a dense arrow, dense row, especially dense column, dense matrix, dense row you can create. So create a dense row and combine it with using a function called level point. This level point is coming from the regression module. Is this clear? Newer concept, level point and dense vector. New concept. So execute. Next, do a random split. Births hashed. This is a hashed vector data frame that we are creating. Now this data frame need to be splitted. Let's take, we'll be using 80% for developing the model, 20% for testing the model. Data splitted, train, test. You can apply a logistic regression model over here. From PySpark MLib classification, import logistic regression with LBFGS algorithm. So logistic regression with LBFGS algorithm, then do a train, dot train. This is the training data set. 10 iterations, run it. Model is trained. Next. This is on the training data set itself. Then we have to apply it on the test data set. So to predict what we have to do, we have to transformation. There is no predict function. Okay. Please remember in Spark, there is no predict function. It is the transform function. So what we do, birth test dataset, do again transformation, and this is a predict. How come predict is there? Is that did they update it? It is transform, right? In older version, it was transform. Yeah, LR model dot transform on the training dataset. This used to be there in Spark. I think with the latest edition, it is see this one. This is used to be earlier. From PySpark ML feature, do this. Establish a pipeline for feature transformation, feed the data, and then transform. This used to be earlier. Right now it is changed to predict. Okay, let's see what it is. So LR model dot predict on the test data set. Okay, and then we do a feature transformation over here. So once you perform test prediction, then do a mapping here to row features. Okay, then this is the classification matrix, binary classification matrix. So basically two metrics we have to look at, area under the ROC curve as well as the so area under PR, precision recall, area under the ROC curve. So 63% precision recall, 80% seems to be decent model, but not very great model. There are different options to improve the model performance as well. Now here, what we are trying to do, MLib also helps you to or allows us to select most predictable features, basically the feature importance that you can do. So top features to train, how to select? So do a chi-square feature selector, feature transformation dot chi-square selector, select 4 best features, then do fit those model on the birth train dataset, then extract the top features from the training dataset, extract the top features from the test dataset. Now here what we are trying to do, this is the train dataset, do a mapping of row label, then create a zip, means create a set function, which is first you get select selector dot transform birth train, then do a mapping of raw features, and second component that should go to zip function is that map lambda function of label point. label point is row 0 and row 1, which is selected earlier. So combine those two values and create it as top features from the training set. Similar kind of function you can apply it in top features from the test set as well. Okay. If you want to see that, you can just do show this is pipeline added object. Okay, collect. Can you see the label point now? This is how the data would look like. This way, right? First is the target value 0.0. This is the target value, which is here I mentioned as 1. Similarly, for the second record, it would become 0. Okay. Then second square bracket. I think slightly it changed. Instead of a double square bracket, so earlier this was square bracket, now it is changed. Parenthesis, within that there is a square bracket. These square bracket that you see, these are the features. You wanted 4 important features. First feature, second feature, third feature, fourth feature. 4 important features, their corresponding values, the target value. Right? So this is the transformed top features test dataset. Similarly, top features train dataset also you can see. Fine. Any questions till now? No questions?
In case of regression, right? Like how would the value will be?
Same way, regression, instead of 1.0, 0.0, it will be a continuous variable. So I have one example. I'll show it to you.
Sure. The steps here are a bit complex compared to scikit-learn.
Scikit-learn and this one, first of all, this seems little complex. Yes, that is true. Syntaxes are also little complex. That is also true. We just have to understand what we're trying to do. Okay, 3-4 important things. One is this label point, vectorization, need to understand. Okay, vector form, dense vector, label point, and binary mapping. Instead of string, if you want to do a binarization, then you have to do using a lambda function, you have to do a mapping. Okay. Now we can use the same data and using a random forest model. It's pretty simple. Random forest, train classifier, top features train, number of classes 2, categorical features info node, number of trees 6, and seed value 666. Same thing here. Using a random forest model, you can publish the area under the PR curve, which is precision recall, and area under the ROC curve, receiver operating characteristic curve. This training completed. Then this evaluation is going on. Because this is one of the complex data set where coded values are there or uncoded values are also there. You have to perform data cleanup. Here, slightly it reduced again. Earlier it was 63%, now it is 61%. Right. So this is again using top features to train a logistic regression model. This also you can do again. So this kind of training you can do. So what are the key takeaways from this notebook? The key takeaways are, in order to create a logistic regression model, we have to do data transformation. That is first important point. Second important point is about label point and vectorization of the data. Third important point is, instead of a predict, we have to do a transform. Okay. Predict also works because that's, I think, a newly added thing to PySpark. So predict also works and transform also works. Clear?
Could you explain the dense vector?
Hmm.
Spark matrix, the dense matrix.
Sparse matrix and dense matrix. That definition. Huh?
No, the dense matrix that you're passing, right?
Hmm.
The labeled point.
Right.
Why is it asking for a dense?
Right. So then if you pass a sparse matrix, the algo understands there are a lot of missing values in the data. That is why, so it is required to pass the dense vector. Dense vector is just a wrapper. Even if your data has missing values also, if you pass the dense vector, then the algo will run. It will work there.
I mean, you are filling dummy data there?
No, not dummy data. It is the real data only, but it's just a wrapper. Just a wrapper.
Possible to bring that with the before and after value of
Dense vector. Dense vector. Okay, I can give you a very simple example here. Okay, so where is the data here? This is separate data. Not a problem. So let's create some data. Some sample data I will create. Now this list will have first set. So let's take you want to run logistic regression. So 1.0, this is the class. Now then you have to apply some features. So features could be, let's take 0.5, 10, 12. Okay, 3 things that we are passing over here. Okay, this is fine. This is fine. Put a comma. Second record. Second record is, let's take 0.0. Sorry, comma. Then 0.7, 12, and 120. Some sample data. Okay. Then put a comma there. Come back. Then you do again 1.0, comma. Then some numbers 1.5, 21, 35. Put a comma. Then create one more new line 0.0. Then 2.3, 45, 98. Let's take some sample data we created. Okay. Now I want to convert it into a Spark data frame. So I'll call it a df spark dot create data frame on this data. Now what I will create here, I'll create a target, which is your objective that you want to make a prediction, and you call it features. So Spark data frame now created, and here you can just do show. This is how the data looks like. Clear now?
Yeah.
I will change the numbers. It becomes, it doesn't matter whether it is a sparse vector or a dense vector. It really doesn't matter at this point of time. So here we did not do any kind of sparse vectorization and dense vectorization. It is just data as it is. Clear? Now, what I would like to do is I would like to do a test on this. So let's take, I will say spark dot no, before Spark I have to do a chi-square test, right? So from PySpark dot ml dot start import chi-square test. So I have to perform a chi-square test on this. So this module is imported. Then this dot test. Within test, I have to provide this is my data frame that I want to test, and I want to test features and label. Those two things I want to test out. Column features must be class type this beautify. Okay, now we can see the error over here. See the error. What is this error all about? Test cannot be performed, right? Illegal argument. Why this is illegal argument? Because linear algebra or linear algorithm, it requires a vector which should be a dense vector. Okay, if your data is not dense, you will find this kind of error. So to correct this, what we have to do, we have to write one additional module over here. Here only we can just write from PySpark dot ml dot linear algebra import vectors. Okay, now I'll copy the vectors, put it over here and do dense. Similarly, vectors dense, vectors dense, and vectors dense. Update. Okay, update the data frame. Now do df show. Now this becomes a dense data frame. So I should be able to run it now. Again some error. Okay, let's see. Label does not exist. Where is label? Did I do? Oh, it should be target. It should be target. Because I named it as target and features, right? Again, some error. No, oh, it's a warning. It's not an error. Okay, so do a head function. We get the p-value of chi-square test. We get the degrees of freedom. We get the statistics required. So this is a dense vector also. Okay. Now, in order to parse this object, I have to assign it to something. I will call it result. Now, what we can do? Result dot. Uh, this is what we did. Square test, right? Statistics. This is my data frame. This is features. This is my. Why this is not coming? P values. It should work. Dense vector is not callable. Okay, cool. What is the other way to do? We get the dense vector here. Okay, but I don't want dense vector. Which object I want? I want the p values. So within this row, I have to get into this row. I have to parse this object and pick up the p values and pick up the degrees of freedom. Both I have to pick up. This assignment we did. What object we are getting here? This is still fine. This is also fine, but it should ideally show as a dictionary. Okay. What do we have here? This becomes a dictionary. If I don't want dictionary, index. No, index will not help me. So basically I need to parse this object to extract the relevant statistics like p values separately, similarly degrees of freedom separately, and from statistics separately. Okay. Now this is the concept of dense vector. We just have to do a format. We did not change any data. Data is as it is. We didn't change it. Only thing is the format change.
So so we have to do the for the features we are passing, right?
Correct. While passing the features, we have to do a dense vector.
It's a mandatory.
It's a mandatory, yes. Otherwise, we'll get errors. This is fixed. I mean, based on PySpark APIs, it is fixed.
Just
okay. Any other questions? No questions? Very good. Okay, so we can skip. Go to the next script. This is another ML pipeline using the same data set itself. So here we are just using the some of the features from the same schema, same data set. We have to pass the path here. Go back to fourth. Get the file path. Go to 5 again. Then feature transformation. Now this is your 1 hot encoder. Okay. This one hot encoder also this, but this one hot encoder is in your PySpark. PySpark has a module called feature transformer. So PySpark.ml.feature has FT. Now FT also has a function called one hot encoder. You could use this, or you could use the other way of doing a map function. Using the mapping function, you could do a one hot encoder. So we are applying one hot encoder here. Then this is important. Okay. So what is this? We talk about label point, right? Label point is a format. Okay. Either you do label point or you apply vector assembler. Both are essentially they does the same thing. There is no difference. Clear? The difference here is in label point, what you have to do? You have to do vector dot dense, right? Clear? This is what you have to do if you are using label point. If you are using vector assembler, you don't have to do this. Clear? Either you do this or you do this. Both ways, the data gets transformed to this. Fine. Questions?
No,
Then
you're fine.
internally,
Sorry.
assembler internally calls vector dense.
I'm sorry. Can you come again, please?
In assembler, internally vector dense has been called, right?
Correct. Here you can define the input column and you provide the list and you provide encoded output column. Call the output column as features, right? This is part of your vector assembler. Then you can create an estimator. Let's take a classification model. Use a logistic regression as a classification model. Create a pipeline. Pipeline means multiple stages. So first you get the data, apply encoder. Then you do a feature creator. Then you apply a logistic regression model. This is the pipeline. Now then do a random split, 70% for training, 30% for testing. You create a train test dataset. Then you do a pipeline dot fit on the training set and model dot transform on the test set. So predict is an advanced, predict is an added thing recently, but transform, please use transform, right? Prediction, we can try this out if it works, but earlier it was transform only. Okay. If you want to predict something, okay, it broke somewhere. Job aborted due to stage failure. Task 0 in stage failed, one item must failure. Okay, what is the issue? Pipeline failed somewhere. Okay. PyForge Java error. Okay. This is fine. Driver subtask issue. This is okay. Did I run the pipeline? Okay. To apply. Again, the same error. Stage failure. I think this is some issue with the space. Let's refresh. Storage is fine. Enough space. Two tasks failed. I'll start from the very beginning. And I think this is due to cluster error. Here I can see internal executor driver issue. This is nothing to do with algo, nothing to do with function or data type. Seems to be some issue with the driver itself. Maybe we have to terminate this cluster and start it once again. But please try this later. I'll skip this part and proceed further. Model performance will not run obviously because we have not trained the model. Then saving the model, you can save the model as a pipeline. Load it from the pipeline and again make predictions. This part is hyperparameter tuning. Okay, let me first detach this cluster, restart. And restart the cluster once again and try to run this once again. Let's see. 'Because these concepts are also very much important. If after this it doesn't work, I may have to delete this cluster and set up a new cluster. So maybe we can take a break here. By the time I set it up, you guys can take a break, please. 15 minutes?
Yes.
Yeah, okay. Let's connect at 4:15.
Yeah.
Okay. I'm just trying to fix it. Please take a break.
ಅದು 20,000 सब्सक्राइब कीजिए।
Hello everyone. I hope everyone is back now. Okay, so this seems to be this error that we are getting. It is could be a data error because now I am just rolling out the infra related error because it is breaking either during this transformation somewhere some issues is there in the data, or in the raw data it may have some issues. So first let's rule out the issues in the raw data itself. So to do this, first we have to check the independently all those columns separately. What is the issue? Okay, so what we can do now, birds dot select, and we'll select one column at a time. So what I can do here is birds dot print schema. It gives me all column names. First I'll copy this column, paste it over here. I want to see all the distinct values. Okay, dot show. This is the issue, because here all the values of this column, how can it be null? This is absolutely not possible, right? This is one. Okay, let's try out others. Birthplace. This is fine. Okay, let's first remove this from the data itself. So what we can do now here, this is labels, this column is there, so I have to delete that column. So this is, I'll call it raw data. You read all, create births equal to raw data drop the first column. Okay, now it is dropped. Just check now, and I will just place this now. Doesn't exist. Fair enough. So now birth data is being print schema. The first column is gone now because all the values are null. So if some values are null, you could just do imputation. All values null means there is no point in keeping that. This is fine. There is no question mark, no junk values, nothing, which is okay. Now this one, others combined age 1, 2, 3. This is fine. CIG before. Okay. Genuine. All the values are genuine. There is no issue here. This is CIG before. Similarly, check this one also. This is okay. Similarly, distinct gets all the unique values from this particular column.
Okay, which are the unique values completely?
Yes, yes. Which are the unique values appearing in that particular column? Yeah, 99 is there, which is okay. It is a coded one, but it is fine. Then the first one, sorry, next one. This is also okay. Then check this one. This is also fine. This one also we need to verify. Things are fine. This seems to be fine. Next is weight gain. This could be having some issues because 0 we can see, but still it is okay. It should be okay. Yeah, it should be okay because it is not null. Not null. 0 is still fine. Diabetic spree. This is still fine. Yeah. Gestational diabetes. It is fine. Yeah. So what I'm checking is that if there is any null value in any of the columns that actually creating trouble in training page itself. So this should have been checked before because I didn't check this and proceed with this. That could be the issue. Yeah, this is fine.
Even one null will cause problems?
Yeah. Even one null also could create problem. So null value need to be always replaced either with a 0 or average of that column or something else. You cannot have null. That is why first column we deleted. All the values were null. This is hypertension gestation. Hypertense gestation. Previous birth preterm. Perfect. All the columns seems to be fine. Now we can proceed further. This one I can delete. Social not required. Delete. Delete. Okay. This is fine. Go ahead. This is okay. One hot encoding. This is vector assembler fine. Import classifier. Find alignment report. Is that? Where is that column? Infant. Oh, this one is the target column. But why would the target column would have everything as null? That's a problem because here, even if I see here, label column is infant alive at report. It is missing. Fine, so we'll make something else as a label column or target column. We don't have a binary thing here. Oh, interesting. Let's do once more. Import raw data. If it is integer, then why it is showing select? There is nothing in this. Why? Show. See, all are null. How come it is possible?
Can we get a dummy value for 1 zeros?
Yeah, I'm just thinking. But dummy value, how can we replace it? Because we don't know whether the person is, whether the infant is alive or not, we don't know. So on what basis we are going to impute the values? That's a challenge. So this is, yeah, it's a data problem maybe. We can skip this maybe. Okay, so let's look at, because see, if the target column is missing, there is no point in doing further analysis. If we manually fabricate it like 1 and 0, even if we don't know, manually fabricate it, it is like there is no point. Accuracy may go for a toss. So whatever we are doing further analysis, it is lost, right? So let's not look at this. Let's proceed further with other things. Okay. This doesn't make sense till here. I have to check the data because if there is some other data which may have
Diabetes pre-post.
we can diabetes pre-post if we have to use as target column.
I don't know if it is 1 or 0, we can use that.
It is not 1 0, but still, if you are saying, I can check that. No.
No, no.
So we don't have any binary column in this.
There was one more data set, right? The transformed diabetes data set.
Transformed one, where it is in this?
Yeah, I mean, in your table, you had two birth, basically, data set. Can you go to the data set?
Okay, okay. This one?
Yeah. Can you try this? I mean, let's see whether we have something in this.
Okay. Copy. This one is fine, I think. So let's check the distinct also for this. This is correct data. Thank you. We could use this one. Okay. So I'll replace this. I will call it births. This one we can delete. This is fine. No, this one we can change it to births. So we have 0 and 1. This one we can delete. This is okay. Print schema. This is fine. Feature transformation. one-hot encoding, vector assembler, classifier, run logistic regression model, run the pipeline, data train test split, train the model. That's working. Okay, model completed. This is about prediction. So here you can say actual is 0, predicted is 1. So it's a misclassification. So we can check the classification accuracy. (73). Area under the ROC curve. On the test data set, evaluator metric name area under ROC. Evaluate metric name area under PR, precision recall. Okay, fine. And we can save the model in the file location, file path, and we can store this. So pipeline write, overwrite, save pipeline path. Now, once the pipeline pipeline is being stored, we can import, load it back, and then do a prediction. So pipeline.load, this path you are storing here, you can use to load the pipeline to current session. Then you do a fit on the training data set, then predict on the test data set, and take one prediction.
What is the take one?
Take is like head.
Oh,
Head function, show one, head one, like that. Okay. Similarly, here pipeline, this is model path. You can save the model, load the model, and predict using test dataset. Okay. Now there is some issue here as well. Let's see that. Load pipeline model path. Again, what's the issue here? Path must be absolute. Okay. Data path issue. Model path. Here we did not face an issue. In fact, one-hot encoder logistic pipeline. Logistic pipeline model. So what's the difference? Pipeline model load. Here also we did pipeline. It should be pipeline.load. Load pipeline. Pipeline is the function, it is not the object. So it should ideally work. What's the issue again? PySpark import pipeline model. What's the issue? Here what we're doing pipeline.load, pipeline path, and loaded pipeline. Then you are doing fit, transform, take. Here it is having issues. Okay. This is my pipeline path. Write, overwrite, save pipeline path. So what's the difference here? These are pipeline objects. Metadata, stages, having some path issue. Expected pipeline, but found class name as pipeline model. Where is pipeline model? Okay. This one.
No.
This is fine. This is just a name, which is okay. Again, it's breaking. Where we're using this? This is working. Let's try once more. Yeah, it is working. What's the difference here? Here we are calling it pipeline path. Eject. It should be pipeline.writer.
The model should be
Pipeline.write. Overwrite save model. It should be the case. This is the model path. Okay. Let's try this.
should work.
Again, okay, this is fine. Loaded pipeline transform. Okay. Pipeline object has no attribute transform. I think we have to use this one. So you have loaded pipeline and loaded pipeline fit on this birth test. This remove it. This is fine. And we can remove this also. Perfect. It works. Okay. Next thing is about hyperparameter tuning. So PySpark has a hyperparameter tuning function also. So PySpark.ml.tuning as tune, and then we can decide. This is important. The param grid builder. This is important. So here we can add, for each hyperparameter, we can add a grid. This is significant. The syntax is significantly different from what we used to do in scikit-learn. So here it is the model object, CL, logistic regression, label column with the target column is this. To initialize this model, then you have to do a parameter, hyperparameter tuning. So tune.param grid builder, this is the function. After that, you just have to add additional grids. Logistic max iteration, it can be 2, 10, and 50. Logistic regularized parameters, it can be 0.1, 0.5, 0.3. Instead of 0.3, make it 0.1. And then finally, just to build. Then evaluator function you can call, because each time you take a combination, max iteration 2, regularized parameter 0.1, and it should be able to evaluate the model once again to see what's the accuracy. Okay, so then we have to use tenfold cross validation. So tune.cross-validator, estimator is a logistic regression model. Parameter grid is stored in the grid function, grid object over here, and evaluator is evaluator. So we have to run a k-fold cross-validation over here. Then within the pipeline, you provide the stages and build data transformer here. After that, use this. So what is data transformer? This is nothing but pipeline fit on the training data set. Then you do cv.fit on the data transformer, dot transform on the training data set, run a cross validation. So you'll get a cross validated model over here. Then from that cross validation, you'll be able to get the results on the training data set. So each cross validation set would be providing one accuracy level. One is the area under the ROC curve, the other one is area under the precision recall curve. Okay. These many jobs running. Done. Then we can print the results. Perfect. So the best model selected from this cross-validation grid search has area under the ROC curve 73.5% and precision recall curve age 72% on an average. Okay. Now the results display is also very important here. From this CV model, we'll get average metrics. We'll get the estimator parameter mappings. Both we have to extract. So this is a function to extract the results. Now this model object, the CV model object, it has all the key metrics while running the cross validation. So what we have to do, first we have to get a key name and parameter value like max iteration, let's take 5. For key and parameter value, create parameter key and parameter values as a zip, which means it will tell you the set and the metric associated with it. Now for parameters and a metric, again get the parameter mappings and metrics together, again create a zip, which means a set, another set. Sort it and so on. So the best accuracy is 74.12 generated from max iteration 10 and regularization parameter 0.01. Clear? Fine. Next thing is about it's just validation. So using a chi-square selector to select the only top 5 features. This is about feature selector. Some additional script around the feature selection. Then you can use the limited features to do a cross validation. And after that, you use the model training, test on the test data set, and then print the accuracies. Okay. So this is one way of implementing or writing the PySpark pipelines for implementing a machine learning model, which is a binary classifier. There are other ways also. So we'll look at now other ways of, okay. Limited features, the accuracy drops significantly, which means we should not be deleting the features. I mean, we should take all features. We should not take only few features. Clear? Then few more functions relating to NLP, natural language processing. You can do regularization here, input and output patterns. Using regularized expressions, you can just tokenize it, and you can do tokenization and see how its sentence is being broken into multiple keywords or token words. Then we can do stop word removal. That's also another part of natural language processing. You can do transformations also, stop word removal. Now n-gram means number of words together. So bigram means n equal to 2, which means 2 words at a time. Trigram means n equal to 3. So n gram, bigram, trigram, 4 gram, 5 gram, 6 gram, etc. 6 gram means 6 words together, one go, right? Now somebody is telling parameter hyper tuning. Somebody is saying hyper parameter tuning. This is 3 gram, which means feature transformation n gram, n equal to 2. Stop word, you need to remove it, and after that you just have to compute the n grams. Okay, so this is some feature transformation and printing the n grams after that. Then this is important. This discretization of a continuous variables. This is very, very important because sometimes the numeric column that you may have, it may be skewed. Either it is positively skewed or it is negatively skewed. So in those cases, you have to create buckets, which is also known as discretize. So basically band. Now let's take you have a customers database. The age of customers could be like 10 years to 80 years, right? Now, if I want to create 5 buckets out of it, so how do I create it? Right? We can look at some real data and do this discretization also. Okay, so let's look at some real data. We had this births data set, right? Print schema. Which column we should take? Let's take pre-weight, mother pre-weight. If I just take this column,
Mother age.
Age, okay. We can also take that one. Where is that? Where is that? Where is that? Where is that? This one. Okay. Sorry. So this is the column which is continuous, and you have to discretize this, right? So to discretize this, what do we need? This is hypothetical data, X, Y, hypothetical data. Then you are creating a schema and then you are attaching it, right? Which we are not going to use. Okay, we are simply going to delete it. We want to use the real data over here. So what we can do, first, instead of doing this, I will assign it to one column. So I'll call it data, which is equal to births call data frame. Select one column. Now this becomes my data. Now here I have to import the quantile discretizer. This is a function. So from PySpark machine learning dot feature, sorry, dot feature import tab. So when you import tab, then you will get binarizer, which means it will only create zeros and ones from existing features you can define. So we'll also cover this one today. So there is option to do, where is that? Where is that? Quantile discretizer, so Q, right? Where is that? This one. Quantile discretizer is something, and also we can use bucketizer. Okay, these two modules you have to import. Then feature transformer dot quantile discretizer, or you can, because since we are importing here, I'll just remove this feature. So quantile discretizer, number of buckets 5, input column here I can say is going to be continuous variable. It should be data. Output column should be data discretized. Data underscore discretized, but this is data. Okay. No, this should be as it is. Will not change it. Just a discretizer. This is a continuous variable. This should be discretized. Okay. Now discretizer dot fit on the data. Transform the data. Group by discretized. Mean of continuous variable. Sort discretized. Collect. Continuous variable does not exist. Available mother age years. Okay. So we will call it mother years. And this also I'm going to change. Perfect. So 5 buckets we have discretized. Is it clear?
Yeah, it's based on average age, right? 19.
No, no. This is not based on the averages.
We see that discretized the data.
Which one? Sorry.
The discretized data.
Discretized data. This one.
Final after the buckets, 5 buckets.
We want to see that. Okay.
Yeah.
It should be shown.
for each of them.
Sorry?
It will assign a bucket type for each of the years, right? Okay.
Okay, now let's look at this. This is quantile discretizer, right? Which means 20 percentile. First 20 percentile, second 20 percentile, third 20 percentile, like this, so on and so forth.
Yeah. So it's creating a bucket of five, like 0 to 5, and then whether it falls between 0 to 20, then it goes into zero like that. No, not 0 to 20, like 16 to 20.
No. Quantile, what is quantile? Quantile divides the distribution into 100 equal parts.
Yeah.
Right?
So over here it's creating into five, right? Splitting into five.
So
Yeah.
0 to 20 percentile, 20 to 40 percentile, 40 to 60 percentile, 60 to 80 percentile, and 80 to 100 percentile.
Yeah. Okay.
That is why. So once the percentile mapping is being done, then the data would be having a number. Now this is in first quantile, this is in second quantile, this is first, this is second, this is third, this is fourth. So that's why 5 quantiles are being, so 0, 1, 2, 3, 4. You can see 5 quantiles, each record is being mapped to each quantile by its position. Okay, then it is discretizing. So what is quantile? Quantile is nothing but it arranges the data in ascending order, right? 20 percentile would be, again, total number of records divided by n multiplied by quantile. I did that calculation.
Yeah.
This is where the quantile calculation I was showing somewhere, right? I deleted that. Okay, so quantile is nothing but arranges the data in ascending or descending order, and it picks up the nth number. So what is the total number of records in this case, in this data set? Here we did head 10, first 10, tell. Last 10. Okay. So once the bucket is being assigned, it picks up the ages and it computes the average of it. Clear now?
Yeah.
Okay. Similarly, continuous variables, we have to standardize it, which is standard normal conversion. 0 mean standard deviation 1, which is like a standard scalar in our scikit-learn library, right? Here also we have a standard scalar. So we do input column, you can just paste it over here. This is the normalized pipeline. Okay, so we have to change this. Input column should be this one, and this is input, and this should be output. Oh, sorry, it's not data discretized. It should be mother age years, right? It should be mother age years, mother age years. And this is vectorizer, standard scalar applied, normalized. Perfect. Now run this. Okay. Mother age year variable does not exist. Why it is not existing? Okay, it's input column, right? So it will not exist. Okay. So it's done. So data standardized. Now we can see the standardized data. Copy and add a new line. Dot show 3. So this is the standardized one. Actual column, vectorized column, normalized column. Clear? Any questions on this?
Is that vectorized column?
What is that vectorized column?
And we are only taking normalized columns.
No, see, normalized column we just appended to this particular data frame. Vectorized form of the column would be required when you are why we are using vector assembler, because this would be required in model training step itself. So next, if we are going ahead with model training, random forest classifier or something, we may have to standardize the data. So here what we are doing, we are adding a new column here, making the data type, doing random split once again, and again we are running this model training on random forest classifier. Okay, so we can standardize the data and normalize, and then we can check the accuracies once again. Improved little bit, not much. This is again decision tree. We can try and print. Decision tree is far better. Okay. Clustering, you already know, I don't want to cover it here. Clustering, we can cover it later at some other point. Regression here, using the same data set, some of the features we can create, and again, vector assembler and chi-square test feature selector both would be required to run regression models. This we can run right now. And we can use gradient boosting regression model over here and generate a prediction here. Feature creator, selector, regressor. Three things. You can just fit a pipeline and run it. And finally, you can print the accuracy. Pretty bad. R square is pretty bad. Maybe this dataset is not for regression. This is just for execution of some sample thing, which is okay. Okay. So you know how to run linear regression, logistic regression, feature transformation, grid search for model training, hyperparameter tuning, storing the models, saving the models, right? And performing various transformations. All those things we covered in this notebook. Anything else I forgot, or anything else you want to know more?
Can we get a confusion matrix here?
Confusion matrix, a very good thing. Let's see where it would be. Model performance. Evaluation. This is evaluator. Metric. Import PySpark.ml dot evaluation as ev dot confusion matrix, where it is. Multi-class classification. No. Okay. This is multi-class classification confusion matrix. Where is confusion matrix here? Vector assembler, decision tree classifier. transformations, multi-class metric. Okay, this one will be required. Okay, multi-class matrix. Then we need what do we need? We need predictions. We need the actuals, right? Predictions and labels. This one also we need to run and print. Prediction and labels. This is binary classification evaluator. This. No, it is not going to be useful. We are using test model. This is the predicted data. Test underscore model on the test data set. Okay. Test underscore model or RDD map tuples. We get the matrix dot confusion matrix to array. What is the issue? Use parse spectrum. Okay. Matrix confusion matrix. Okay, two array is not possible. Let's remove this. Again, the error. Matrix. It's working. Okay. Next step. Matrix dot accuracy confusion matrix. Okay. Confusion matrix. So it should be working fine. But there is some issue here. Does not match with the length of the fields 3 full traceback, which means what data it is having. Multi-class object has no collect. Okay. Show has no show. Okay. Very good. It is just an object. Okay. Call confusion matrix, precision recall. So many things are there, but why it is not accessible? Sorry, I think we need to figure out what went wrong here. You just have to check. Ideally, it should work because what you are getting. Okay, let me check. What do we have it in the test model? It is important. Test model has, okay, show. Oh, so many things here. Okay, that is why. So then we need prediction and prediction label. So what we need, test model, select, we need prediction, and we need a label. Where is the label? Infant alive at report. That's the label, right? Do we have any label column also here? No. Features, raw prediction, probability prediction. This is the label thing. Okay. Now this part, we can take it over here. Just check. Perfect. This is prediction. This is actual. So we have it now. instead of doing this, I will pass this to this, then matrix dot confusion matrix. It should work. What happened again? Okay. Okay, fine. Let's remove this part. At least this part is working. Next step is I will use this one. So tuple, prediction, confusion. So I'll call it 1, matrix 1. Okay. Why it is an error? There is some error.
Prediction is float.
I'm sorry.
Prediction is float. Float.
Prediction is a float. Ah, okay. That we need to change. Okay. This is prediction dot select. Else it won't work. Okay. Predictions. Okay, where is the prediction?
Should type that other one.
Transform predictions dot select. So in this case, it should be test model, which we are using. Test model predictions D with column label. This is label. So instead of this, I'll put label. D food type. Added by prediction. Okay. Predictions. Somewhere we are using. It should be prediction. Now D does not exist. I am selecting D here. With column this. This is not required. Close. Float type. Remove this. Order by prediction. There's something wrong in this. Okay, I can share this link or maybe just do a little bit of research on this to figure out. This is scikit-learn, which is not required. PySpark 1 is required. You do a prediction, you get label column as D. This is featured. Okay. So label column need to be changed that. Okay, so the D is nothing but the label column. Predictions. This is the D part of it. F is not defined. What is F? Functions. float type is not defined. Nice. Okay. Okay. Now it worked. Next. Again, what's the issue? Matrix 1 predictions and labels. This will have. Why it is not changing this? We selected two columns with column this and column this cast as a float type. Order by prediction. Okay. This is fine now. Yes. So finally done. Okay. Any other questions?
So that in the discretization, so you do that quadratic discretization, right? So when you set it to 5 bins, after setting the 5 bins, you put each of the age in particular bins, right? And what is the criteria for based on the age, right? Average age.
Not average, quantile.
Yeah,
Quantile.
in this case, what would be the point, like 0 to 20, 20 to 40, like that?
No, this is quantile. 0 to 20 quantile. Quantile value is what? That is what it depends. No? See, what is quantile? So let's get some dummy data. Okay. So I don't have any dummy data. Let's see. Do I have any dummy data? Let's take area. I'll pick up this column. Sorry, I'll paste it here. What happened? Okay, so this is the area. Now I want to compute the quantile of it. Okay, so quantile means 20th percentile. Quantile divides the distribution into 100 equal parts, which means first, what is the n? N you need to count, right?
Okay.
N would be total, take the references, 200 records total. This column need to be first sorted in ascending or descending. So it is now in ascending order, it is sorted. 210 records total. So n is this. Now you want to compute 20th percentile. So 20 multiplied by n divided by 100. 42, which means 42nd observation is your first quantile. So you start from here. Okay. 1, 2, 3, 4, 5, 6 like this. You go on. 36, 39, 42nd. So this is your 20th percentile.
Oh.
Now 40th percentile. 84. So 84th observation is your 40th percentile. So this is 42 like this. Okay. So I'll get a number every time. Now 60th percentile. 126th record is your the value. Okay, so here what you can say equal to B126, which is 15.11. 15.11 is your, like that you can just compute. So you start with this way: 20th percentile, 42nd record. 42nd record starting. Okay, I'll just delete this one. So you start from here, which is B2, 40th, 42nd, which means 20 percentile is basically nothing but 42 plus 2, 44. So B44 is 12.08. This is 20th percentile, right? 40th percentile, which is going to be multiplied by 40, 84th percentile. So 84 plus 2, 86. So this would be B86. Now 60th percentile, which is going to be here 126. 126 plus 2, 128. So B128. 80th percentile would be again 80. 168th item, so plus 2, 170, B170, right? And remaining 100th percentile. So 100th percentile is you just multiplied by 100, 210, so 200th and 12th. So B2112 or 211. These are your percentages. So basically the range would be 0, 0 till, it's not percentile, it's a 0 number, 0.00, zero till 12.08. So from this till 12.08, where is 12.08? This is 12.08 till here, right? What is the average? 11.34, right? So this is going to be bucket 1, and remaining these are the 5 buckets. This is going to be this till this, okay, like this. 0 to 12.8, bucket 1, 12.8 to 13.45, bucket 2, like this, so on and so forth. Is this clear?
Yeah. Thank you, sir. Yes.
Okay. So that's all. We can close today's session.
Sure, sir. Thank you.
Yes. Notebooks 1 to 5, I will share it. I'll download it and I'll share it.
I think the birth CSV as well, Pradeepta.
Yes. This calculation also I'll send, and this book to this one, this CSV.
No, not this one. The birth data.
Birth data CSV. Let me check. This one, transformed one.
Yeah, either the transformed one.
Okay, sure. I'll send it.
Yeah.
Okay. Thank you. Thanks everyone.
Thank you.
Yeah.
Thank you.
Bye-bye. Yeah.
Thank you, sir.
Yeah.